Hello student, to the course for Foundation of Classical Electrodynamics. Under module 4, today we have lecture number 62 where we discuss self and mutual inductance. So, we have class number 62 today. And in today's class, we will going to discuss the self and mutual inductance, but before that let us quickly discuss what we had so far. So, if we have a current loop like this and if we throw a bar magnet, then there will be the change of flux. There will be a change of flux, and this change of flux give rise to a current here, and this current will be such that it will go to oppose the motion of this bar magnet. So, in this case the current should be such that, so the magnetic field here in this direction due to the magnet and the magnetic field due to the current should be in the opposite direction. So, that means I should have a current flow in this direction. Okay. So, they will they will be opposite, so that you need to do some work. This is the Lenge's law, last day we discussed. Now, today we will so then the EMF will going to generate, and this EMF is called the electromotive force. So, this electromotive force, if I now calculate that this the general description of this force, force is this. It basically generates something called EMF in short. So, F dot dl divided by q. So, that means this is the amount of work per unit charge on the test charge that is carried around the circuit. So, around the circuit, the force that basically the work done to move the test charge around the circuit is eventually and for per unit charge of that is eventually the amount of the electromotive force, and that is the way one can write. Now, if the circuit is closed, so the expression one can write is this: there should be a closed integral, and I should have the same expression f dot dl divided by q. By the way, here f is the force experienced by the charge. So, this q multiplied by E plus V cross B. Okay, that is the force on the charge q. Now, if I want to find out what should be the EMF for the motion EMF for the circuit which is moving in. So, suppose I am having a circuit. So, that circuit is moving in an external electric field. So, these are the external electric field. So, let me so, in this external electric field it is moving, then we should write here that the rigid wire loop C moving in a magnetic field which is not uniform, which is steady but not uniform, which is not depend on time, but may be a function of r. So, it is moving. So, the question is what will be the EMF? So, one expression that I just derived, so that I am going to exploit here. So, EMF should be closed line integral f dot dl divided by q. E is not here. So, f divided by q I should write as v cross b dot dl, and then closed line integral. So, that I can write in another way, that closed line integral b dot dl cross v. This is another expression to find out what is the EMF of this system. So, one application of this expression, whatever the expression I wrote, is called the Faraday Dix generator. So, let me quickly discuss the principle of that. So, it is called Faraday disk generator. And here what we have a disk like this. This is made of a conductor, and suppose it is rotating with certain angular velocity omega. Okay. So, this is the EMF that we are going to generate here by the way I derived in the last page, that E is integral of B dot dl cross V. So, now dl cross V. So, if I make a top view of the system, then what we have is, this is top view. By the way, so it is rotating, but it is, I forgot to mention that it is in uniform it is rotating in some uniform some external magnetic field. So, magnetic field is already there, obviously the magnetic field should be there, and in the environment of this magnetic field this stuff is rotating. Now, since the magnetic field is there and it is a conducting material, so it will going to be the free electrons there will going to experience some kind of force, and that force makes this free electron the separation of this charge. So, if I make a top view, you can see that. So, suppose I have a small section here of the disk, and from here to here, say it is r, and this portion is dr. The velocity will be along this direction, and magnetic field is perpendicular to the plane B. Okay. So, now you can see that the V cross B. So, what is the force? The force is B cross, the force here is V cross B, and due to this force there will be separation of the charge in the rim area and in the central area. So, there will be a separation, and that leads to the EMF. So, we will need to calculate this EMF. Anyway, we already have the expression of this EMF. So, from here we can readily calculate. Here dl is nothing but this dr. So, I can simply have, and they are perpendicular to each other. So, I can simply have, and B is also perpendicular to the disk. So, this expression simply gives us integration of B omega r dr. Omega is the angular speed, and I can replace this V to omega r, and since they are this dl is equivalent to, here dl is equivalent to dr. So, I can simply replace this expression in this way, and if I integrate, the value is half of omega b and then a square, because I need to integrate this stuff from 0 to a if a is a full radius. Okay. So, now so let me draw the system once again. I have this conducting disk, and it is rotating along its axis, and the magnetic external magnetic field is there. So, it is rotating in the environment of external magnetic field B, and this is rotated like this way with a angular frequency omega. Now, what happened that it will already there is a separation of the charge, and that leads to EMF. So, if I want to I mean, if I just have the circuit here, if I complete the circuit, if I join this part and this part, if I complete the circuit, then there should be a flow of current, and this current, if I say I, then I will be simply whatever the EMF we have, that is half of W half of omega B square and divided by the resistance R. So, this is the amount of current. So, if I increase the amount of current, then what happened that I can increase the area the radius of this disk, which is A. So, this is the area, or I can increase the amount of angular the rotation, and under that environment what we do, that we can able to generate some current. So, this kind of system is called the Faraday-Dix generator. So, I just exploit the expression of EMF that I discuss, and then exploiting that I can have the expression of the current. Okay. So, now let us move to today's topic, which is the self and mutual inductance, and we are going to calculate few things out of that. So, let us try to understand fact what is the meaning of that. So, next we will discuss about the self inductance. What is self inductance? So, if I have a where the current is flowing, because of the flow of the current, what happened, it will produce some kind of magnetic field, and that magnetic field will going to cross its this area, because of the current that is flowing in this loop itself. So, this is the B we are having. Because of the flow of the current of the loop, it will going to generate some magnetic field, and that magnetic field itself will going to cross this. So, so that means this current will going to link some kind of flux. So, that the flux linked with the loop the amount of flux that is linked with the loop is simply proportional to the amount of current. So, if I write this flux is phi b, so phi b will be simply proportional to the amount of current that is flowing in the wire. And if I put the proportionality constant, then phi b is equal to the proportionality constant multiplied by I. This proportionality constant L is called the self inductance. This is called the self inductance. So, here the quantity L is called the self inductance. So, what is self inductance? The total flux linked with the unit current flow, and the total flux phi v linked with the unit current flow. So, L is eventually phi b divided by I. So, the total flux linked by unit current flow, the total is defined as L, the self inductance. Now, if I calculate this, so we know that this is EMF is phi v divided by dt. So, that quantity for self current is minus of d dt of L I, and we simply have minus of L d I dt. Okay. Now, this is the way we define, and now we can calculate what is the self inductance for a solenoid. The standard this is the standard problem. So, what is, then maybe we can have some idea. So, now we calculate the self inductance self inductance of a solenoid. So, for solenoid, so we know that what is the, I mean, quickly if I draw the figure here. So, we have the current loop, like this. So, the magnetic field that is produced in this core region, this magnetic field that is produced, the magnitude of that is mu 0 n I, or if I write in it with the total number of turns, then it should be mu 0 total number of turn multiplied by I divided by the total distance L. L is the total length of the, so this is the length of the solenoid. Solenoid. So, what is the amount of flux linked with this magnetic field? So, the magnetic flux that is linked is simply the B multiplied by the area, and the area is N A. A is the area of the single loop and N is the total number of loop. So, it should be N multiplied by A. So, that gives rise to mu 0, then N square A, and then I divided by L. Now, the mutual inductance, if I want to calculate for this, then L will be simply phi B divided by the current I. So, this quantity is simply mu 0 n square, then A divided by L. So, A is again, I can write in pi of say r square, if r is the radius of this solenoid. So, in some cases, so I can write it is mu 0 n square, I have a pi here, divided by L and r square. So, in many labs these experiments are there. So, the student need to calculate what is the dependence of the what is the dependence of the self inductance with the parameter of the given solenoid, that like the L is given. Suppose the value of the L is given and the area they can calculate, this is the area, area is say A, and number of turn is, total number of turn is N. So, this is the way it can depend. So, it inversely proportional to the length, that means if the length is short, then the self inductance should be high. It is proportional to the value of the proportional to the value of the square of the number of turns N. The number of turn increase, then it will going to increase, and it is also square the radius. Another thing we have, since we have self inductance, it is quite common that we should also have something called mutual inductance. So, unlike one circuit, here we have two closed loop, one is say here and another is say here. So, now what happened that for this loop I can have a current flow I 1. So, this is loop C 1 say, and another loop says C2. So, I am having a current flow. So, I need to draw this loop properly. And because of the flow current flow I1, because of the flow of the current, we have a magnetic field that is produced, and this magnetic field will going to cut the other wire, other closed loop like this. So, it is going to cut, but the magnetic field that is produced by the other loop. So, phi 2 is a flux. So, if I now define the amount of flux that is here is phi 2, this is the flux through loop C2 due to the current I1 in loop C1, that is. So, phi 2 again will be proportional to I1, and that give rise to a proportionality constant, and I can write that phi 2 is equal to M21 I1. Okay. Similarly, I can have phi 1 is equal to M12 I2, that is the amount of, suppose I have now the current is flowing in C2, and because of that some flux will be there in C1, and that flux, if I write phi 1, that should be proportional to I2, and the proportionality constant should be M12 in this case. Now, this M21 or M12, M21 and M12, this is the constant quantity, and these are called the mutual inductance. This is called the mutual inductance. So, the E2 that is generated now in loop 2 is minus of d phi 2 dt, that is minus of M21 d I1 dt, and E1, that is the EMF generated in loop 1, that is due to the current I2. So, I can have this is equal to minus of M12 d I2 dt. Okay. So, after having the rough idea of mutual inductance, now we are going to calculate something which is called the Newman's formula, that how they are related and under what condition, and we saw some interesting thing there. So, next what we do is calculate the mutual inductance again, but in a different way. And the formula is called the Newman formula. What was that? Suppose we have two arbitrary loop, one is like this, and another is, maybe I can do some different color, another is. So, these are two arbitrary loop, and the current that is flowing in this is I1, and this is called, this is loop 1, and this is loop 2. Current is flowing here in 1, and it produces some magnetic field, and that magnetic field, the field line may be like this, it will going to cross here, it will going to cross here like this, I am going to cut the loop 1. The amount of magnetic field that is producing is, say, B1 magnitude. Okay. So, now we know what is B1, because the current flow is this loop, and at some distance what is the B1, that we know. So, so let me first draw the systematically draw these things. So, I had a loop here. So, this is my coordinate system, and suppose I had the loop here, this is my loop 1, and my loop 2, something is like this is sitting here. So, these are the two loops, and if I so this is the coordinate system. So, the small section here, if I draw, say, from here to here, and the length from here to here is, say, R1, and this is this length I call DL1, and this is another section which we call, say, different. So, this section is, say, DL2, and the coordinate of DL2, say, R2, and the distance between D1 and DL this length is our notation, it is curly r, where curly r is R2 minus R1. Okay, that is the system we are having. Now, I know what is my B1, let us write straightway. B1 is mu 0 I1 divided by 4 pi integration closed loop. So, I have a closed integral dl1 cross unit vector curly r divided by r square. This is the magnetic field due to loop 1 at some point, and this some point is here. Okay. So, magnetic flux, so the magnetic flux at loop 2 is how much? It is phi 2 equal to integration B1 dot ds2, and that quantity we know is m21 I1. Okay. So, what is the surface integral B1 dot ds2? That I can write in terms of the vector potential A, and let us write it in this way, dot ds2. That quantity is simply closed line integral, because I am using this closed line integral A1 Stokes theorem dL2. Again, I have A1 is mu 0 I1 divided by 4 pi, that we also calculated. This is a closed line. So, closed line dL1 divided by R. So, I can have like S B dot ds2 b1 dot ds2, which is m21 1 is mu 0 I1 divided by 4 pi, and then we have a close integral, and then A I just simply put, which is like closed line integral of dL2 divided by R dot dL2. So, this quantity I simply write mu 0 I1 divided by 4 pi, and then I have this to integral dL1 dot dL2 divided by R. So, from here if I compare left hand side and right hand side, we have an interesting expression m21 is equal to mu 0 divided by 4 pi and two line integral, closed line integral dL1 dot dL2 divided by R. Mind it, R is R2 minus R1. Now, if I calculate m, so this is the Newman's formula, how to calculate this m2i. So, this expression is eventually called Newman's Newman's formula or Newman formula. Now, few interpretation I can make. One, m2i depends on the shape, size and the relative position, because you can see the relative position R is sitting. So, how the two loop are distributed and how what is the relative relative distance between these two loops are important to calculate m21. So, m21 and the relative position of the two loops depends on shape, size and the relative position of C1 and C2. C1 and C2 are two loops. Say this is say C1 and this is C2. Okay, and another thing also, that m21 should be equal to m12, because if you just replace these in this expression, if you just replace 1 2 to 2 1, right hand side will not going to change. So, m21 is equal to m2 1 2, that eventually tells that whatever the shape and position of the loop, the flux through loop 2 due to the current I in loop 1 is same as the flux through the loop 1 due to to the same current passing through loop 2. So, what happened that if I have a current flowing here, so whatever the it is producing, whatever the field B, in a similar way, if you have the current, the same current that is flowing here I, whatever the field produce, both the cases the value of the corresponding mutual inductance should be same. So, that we find from this expression. Okay, now after having these, we will try to find another important thing that we will do today itself, and that is the energy. The next thing that we discuss today is the energy in the magnetic field. What is the energy magnetic field? How to calculate the magnetic energy in the magnetic field? So, we will do in this way. One can calculate by analyzing the energy balance for an isolated inductor. One can deduce the energy content of the magnetic field. What kind of energy balance we will going to discuss? So, the power, so if you look carefully, the power that must be supplied to maintain a current, say I, in an inductor while the power that must be supplied to maintain a current I in an inductor while the current is changing against is against the back EMF. So, some amount of power must be supplied to maintain the flow of the current, because there will be a back EMF, because we have an isolated inductor, and this back EMF simply E equal to minus of L di dt, and the amount of power that we need to work with is this power, the rate of change of work done, and that is equal to the current with a negative sign obviously and the EMF. That quantity, because EMF is this, is IL di dt, because EMF is this quantity. So, this amount of power in order to balance that. So, the flow of the current in an inductor. So, you can see that W can come out to be from here, W, the amount of work done is simply half of, if I integrate this side with respect to t, then it is half L I square, that is. So, the amount of energy, so this is the amount of energy that is eventually stored in the inductor. So, I should write, this is the energy, the amount of energy stored in the inductor. Okay. Now, I have Li is equal to the flux phi b, and that quantity I write in terms of B, like B dot ds, and again B dot ds I can write in terms of the vector potential A, like curl of A dot ds, and this flux eventually I can write in terms of A, like A dot dl. So, this we have done earlier, how to calculate the magnetic flux in terms of vector potential. This calculation we did it. So, these steps. So, W, the work done, should be half of, I can write it like I into Li, because Li I already calculated. So, it should be half of I, and Li I write integral of A dot dl. So, this quantity I can put this I inside, and I can write it that integral of A dot I, make it vector, and dl, because the vector in the same direction, that of I and L. So, the generation for, this is the expression of the work. So, I can make it in terms of the volume current, and in terms of volume current, I can have this expression simply half of integral. Now, the integral will be the volume integral, and that is A dot j, this I just make it in volume current, and dV. It is line current, I can just simply make it volume current. And now, I am going to exploit the expression curl cross B is mu 0 j. So, W, the work stored, is 1 divided by 2 mu 0, just replace this there in place of j, and I should have something like A dot curl of B, then dV. Now, I exploit the vector identities. This kind of treatment we have done several times in many calculation in electrostatic and magnetostatic. So, this is a usual practice now to exploit these expressions, the vector expressions, and from that we can find something extra, something which is having some physical meaning. So, I can use this A dot curl cross B here, we have this term here A dot curl cross B. So, I will replace it here, and that basically gives me W equal to 1 by 2 mu 0. One term I am having is B dot A curl cross A. So, curl cross A is itself B. So, I am having a term like integral, volume integral, simply B squared dV, and another term is minus of 1 by 2 mu 0, and then I have this divergence of A cross B, A cross V, interesting term, over dV. Now, this divergence of A cross V I can write in terms of, so let me write the first part, this is fine, and the next part I can write 1 by mu 0 and the closed surface integral, and then I should have A cross B over the surface. Now, here you can see this is the closed surface integral. So, I can take my surface according to my convenience, and this quantity A cross B both are having the dependency R, one is 1 by R and one is 1 by R square. So, that means this quantity will going to vanish if the surface is very large. So, this integration should vanish, as A and B both goes to 0 when R tends to infinity. For very large surface, this will vanish. So, eventually the amount of energy that is stored in this system should be, or in other way, the energy of the magnetic field is simply this quantity. This is a very important expression. We will going to exploit this expression again when we deal with electromagnetic theory and electromagnetic energy density. Well, so I do not have much time today. So, let me conclude here. Thank you very much for your attention and see you in the next class.